Okay, so welcome everyone. So let me introduce today's speaker, Bireswar Laha. So he is a postdoc right now with Jeremy Bailison here at Stanford, and he has multiple degrees in computer science, math, and also human-computer interactions. And what he is primarily interested in is virtual reality. So you all have seen Oculus Rift, Kinect, and these kind of devices. So how can we bring people in these kind of immersive reality spaces? And what can we do with those? And what he's particularly interested in is data analysis and also psychology. But he also told me that he designed some games around those technologies for the fun of it and actually won some prizes. But I think primarily today he's talking about his research. So welcome.
Well, thank you, Ingmar, for the introduction. So, hi everyone. Thank you for coming to my talk. My name is Bireswar Laha. I'm coming from India, but I did my graduation, my PhD in computer science from Virginia Tech. And then I moved on to Stony Brook University to do my first postdoc. And then this is my second postdoc at Stanford. So all along, before my PhD also, I had some background in virtual reality. For 4 years, I worked in different companies and also at a NASA lab. That led me to my research in PhD, and still I'm pursuing that in virtual reality. So my talk will center around volume data analysis, which is data sets that we get in scientific domains from various different domains. But also my current focus is in psychology, which I won't be touching a lot, but a little bit. So a brief overview of the talk, a little bit of motivation, and then these three arms of my research, which has been some empirical research, also some design research in 3D interaction, and finally some theoretical work also in virtual reality based technologies. And then finally how these all go together for making some sense. So first of all, let me define what is VR or how I define it. So virtual reality, as we all know, has been quite a lot of hype in recent days due to the movies that we have seen, but also due to Oculus Rift that has come out and bought by Facebook, and it is making a lot of waves these days. But VR is an interdisciplinary field, so not only in computer science, but we also use it in medical biology, in video psychology. Like here in the lab that I'm in, it is a communications lab, and the research is done in psychology, but they use VR as a tool. But since this is a talk in engineering, more like engineering crowd, so I'm giving the definition based on computer science domain. So VR is defined from where I come. It is defined as an immersive, interactive, computer-generated environment. So each of the term is important here. Immersive means that we are surrounded by visuals which completely block our vision, our sound, or other senses in important ways. Interactive means we can interact in real time without any lag or latency that really bothers us. And computer-generated environment means it is generated by some computer graphics or by some artificial means, but not really by any real world feedback. So if there is any real world feedback, it will go more into the AR domain, which is augmented reality. That is augmenting some real world stuff with some computer generated stuff. But VR is completely 3D in virtual world. So as we talk about 3D interaction is important. So in real world, we do a lot of 3D interaction, like not only on a computer screen, we move stuff around in 3D. But in virtual reality, we can do that 3D because we're not constrained to the computer screens, which is 2D, or these kind of screens, which is 2D. So 3D, again, defining more formally, like we do in computer science, it is tasks which are performed directly in a 3D spatial context. So moving from the definition, virtual reality is usually looked at from presence or from immersion perspective of research in many different domains. So what do I mean by this? So when the researcher is more in a psychology domain, they will talk about presence. So VR induces this sense of psychological presence in a completely different environment, and it moves us from reality. So that is a psychological kind of perspective that we get in VR. Immersion is looked at by different components of VR, which is broken down. So it is more of a measurable unit. So if we increase, let's say, the amount of field of view, so we increase the amount of immersion. If we add a spatial sound as opposed to a 2D or a two-way sound system, we add more ambience to the sound. So we increase the immersion in terms of sound. If we add some haptics or if we add some smell, so we increase the olfaction or some other senses. So that is the way immersion is done. Now, of course, you can understand that if there is more immersion, there would be more presence. So there is research right now going on in Stanford and at other places which is looking at if we add one or more factors of immersion, how much presence can be improved and how does that matter in different domains. So my talk today will mostly focus on immersion, but just to reiterate that a lot of work is also going on in presence, more in psychology than in computer science. So moving from that, what is volume data, or where is this data coming from? So volume data consists of voxels and that we get from a ton of different modalities, like we go to a doctor to do CT scan of our body, or we do some MRI scans or PET scans. So that generates data in 3D format, which maps various scalar vector tensor entities at these discrete 3D locations. And these are represented by voxels instead of the pixels that we see on a computer screen. And this can come from many domains, like in medical biology, we scan our body, or we scan in archaeology these mummies, which are like thousands of years old. We understand how people died back then. We look inside the Earth's crust for tectonic plate movements and try to predict earthquakes or eruptions of various kinds. Now we getting the sinkholes. So all of those. In astronomy, we understand how the red shift and blue shift occurs, how galaxies are moving, things like that. And we also scan buildings, like here the Leaning Tower of Pisa is being scanned to look at structural defects. So all these are from different domains, and there are many other domains that generate this kind of volume data sets. And how do we analyze this data? So we analyze these either on a computer screen or on these kind of immersive environments. And I'll talk more about the immersive environments later on, but very quickly, from one of our studies, let us look at what we had. So we were working with this doctor who was looking at these data sets on a computer screen and also at animals like a mouse limb. So this data set that we had was the lower left limb of a mouse, and the typical tasks that they were interested in, looking at the bones, understanding where the bones join, understanding where the blood vessels come from, where they go, things like this. Now with these kind of tasks, talking with them, we found that they had a lot of trouble understanding this in 3D, because as you saw, it was very hard to understand where those things were. So these were the tasks that they had trouble with. And looking at factors which might have caused their trouble, we wanted to look at the fidelity of the system. So how closely the system matches the feedback quality that they wanted to have a better understanding of this data set. So that we defined as system fidelity. Now also talking about system fidelity, if we add more fidelity to the system, how about the interaction? If we still use the mouse as we walk around the data set, in 3D, does that really make sense? So the interaction technique also is another factor that we wanted to look at. And this kind of tasks, we put all of them together from different domains in our task taxonomy, which I'll come to later. So these three were the main focus of our research during my PhD and later on. So what are the effects of system fidelity? How does really 3D interaction techniques matter when we increase the fidelity of the system? And then how do you categorize these tasks so as to make the impact across domains and not only to one domain where we have these studies? So I ran over the years a bunch of empirical studies looking at the effects of system fidelity. I designed and analyzed and also ran some studies with some novel interaction techniques, which I'll talk about in a moment. And then I did some theoretical work on some task taxonomy spanning different domains. So very quickly about the first part of my work, which is into some empirical research studies. So starting with this basic desktop, we have some HMDs that are out there. We also can have caves, which I don't know how many of you know. So have you heard about a cave, which is not like a cave in the real world? Yeah, so not very many. So let me show you another slide, which has a bit more to it. So caves like these or these would be a big projected display covering you, like one I think we have here at Stanford. It can have a 4-sided or a 6-sided or a more like a curved kind of environment where you walk in and you will be completely immersed with surrounding displays, and these will be in stereo with head tracking. So in real world, if I walk here, I can see what is behind this board. In a desktop, I won't be able to do that unless I click the mouse and drag it. But in these kind of caves, or in this Brown's new cave, which is known as this yurt, or in this allosphere, which is a 3-story facility in UCSB in Santa Barbara. And these allow us to just walk around freely in 3D space and look at stuff which is in stereo or with head tracking. So those are some immersive hardware that we have in recent days. Earlier from the desktop we had this tabletop or some display walls like these, or obviously a lot more pixels to those. And this Z-space, which some of you might have heard about, these are like desktops with stereo and head tracking. So all these things are components of display in virtual reality, which has come out recently, and there are more that are coming out. But why am I showing you this slide? So a scientist who is analyzing these data sets and has all these display at his disposal, so which one they would choose and why, right? So that is a question we want to target. And earlier studies which has compared the displays directly in 1990s, what they did was they compared a desktop directly, let's say, to an HMD. So this was one of the first study run in 1993 by Randy Pausch, by the late researcher Randy Pausch. He was a great researcher in VR, and he found that using HMD we can have significant benefits of analyzing these data sets over a regular desktop, which is not head tracked. More recently in Brown, they ran this study where they look at these confocal data sets and looked at 3 displays. So one was a basic desktop, the other was a desktop with a fish tank VR, like they called. So it had stereo and head tracking, very similar to a Z-space device, and a cave. And they found that if you increase the immersion, there is a significantly better analysis of the results that they were looking for. So all these problems that they tried to address were, the results that they found were tied to the systems. So how about all these huge array of systems now? And there'll be more coming out. So if we tie the results to the systems, or if we just limit them to the domains, we are not generalizing the results. So we wanted to have a generic model of running these studies. So we looked at system fidelity, and we broke down these into display, interaction, and scenario components. So display would be how much immersion I'm getting in terms of the visual display. Interaction is how close to the real world or how natural the interaction is. And scenario fidelity is how strong the computer is in generating the computer graphics that we wanted to see. So we separated out these 3, not just sitting. We went to the conferences and spoke to people, and that's how it came out over the years. And these components, during 2000 to 2007, many researchers in Europe and in US, they broke down immersion in these different components. And these are components of display fidelity. And there are other components of audio and olfactory and gustatory and other components, but I'm just focusing for now on display. So some of these you already know. So field of view is how much I have instantaneously. In a real world, I have around 180 degrees horizontal, about 90 or a little bit more vertical. So how much of that I have in the display that I have. Field of regard is in total how much can I see. Head based is whether the head is tracked or not. Stereo, display size is how big the display is. Resolution and realism of lighting. So all these components are separate components of immersion. Now with these components we can really characterize any system that comes out. Let's say the Z-space, it has stereo and head tracking at a higher levels, but the other are lower levels. The reality deck in Stony Brook, you might have known, that has 1 billion pixels, but that has a field of regard and display resolution at higher levels, but it doesn't really have stereo. It might have head tracking based on what applications you run. The YART is getting very close to retina display, which is what our eyes can perceive in real world. So it has all of these components at higher levels. But you can see that if we characterize any system that comes out based on these components, it is a much better way to generalize the results. So what we did was we picked 3 of these components, and we chose data sets from 2 different domains. So this was a mouse limb data set that you just saw, and this was a fossil data set, which is 1,000 years old, actually million years old data set. It's a fossil sample, a tiny sample scanned at the micro level called Parapendorina. And we worked with the scientists to understand what they are trying to address, and can those be understood more if we increase these components. So we had 2 levels of field of regard, stereo 2 levels, head tracking 2 levels. So you can understand 3 independent variables with 2 levels, giving us 8 conditions. We ran these participants who were volunteer through these tasks. We designed the tasks working with the domain scientists, so medical biologist and a paleontologist. And finally, we got a bunch of significant results showing that if you increase the components to some specific levels, some combination of the components will allow you some better results. So I'm not going into the details, but we published this paper at IEEE Transactions, which are at a 15% acceptance rate. So it was a very strongly accepted paper, and quite good citation so far in last few years. So moving from there, we knew that these components can have differential effects if we combine at specific levels, but then how can we generalize them across the domains or across the displays? So this mixed reality continuum, again, this can take a 1 hour talk, but I'll just touch very quickly. So in 1993, Milgram and Kishino published this paper that talks about this mixed reality continuum, which ranges from real world to augmented reality to augmented virtuality, which some of you might have heard recently, and then virtual world. And as you increase the immersion of the display, if you have a really high immersive display, you can really recreate any system on this continuum. So that is the whole idea of MR continuum. Now using this, we wanted to recreate any display based on the components that we had. So again, we recreated our previous result, but we didn't use a cave this time. We used a head-mounted display, but we used the same components of field of regard and I think head tracking. So 2 levels or 2 of these components, giving us 4 conditions as for our empirical study. But then we also varied the system, which is 2 levels, giving us again 8 conditions. And we found really that the results could be recreated, which means that the results are independent of the displays. The results are independent of the systems. So if you have the same levels or the same components, no matter what system you have, you can have similar results, which is a strong case in generalizing these results in VR platforms. So again, not going into the details of this study. So this shows a very quick overview of the 2 cases. So here a participant wore so this was Envy's SX11 HND, which is a pretty heavy, it's bulky and costly, $30,000. Now the Oculus Rift is, I think, $150 and much lighter. And this was a cave where a participant could walk around and see without wearing anything, just goggles. I'm not going into the details of the result, but we recreated many of the results and extended those as well. Again, this was published at Transactions, IEEE Transactions, which shows the strength of the work. But then this raised a lot of questions, like we looked at just one kind of visualization, which is 3D texture rendering. How about the other kinds that there was? So we were working with this theoretical framework, which I'll come to later on. But we had these different visualization algorithms that we're looking at. So not going into the details, again, this is more into computer vision or such visualization, but we wanted to look at isosurface in our next study, and we had looked at X-ray rendering. So looking into if we change the visualization of the data, does that really matter across these different kind of tasks? So all these tasks, again, I'll come to later. So we're working with these domain scientists, and we map these tasks in this kind of umbrella of task taxonomy spanning different domains. So next we worked with a biomechanics scientist who was looking at these small beetles, carabid beetles, and then he wanted to look at how the tracheal tubes in these beetles branched off in different directions, and what it means if it branches in 2 as compared to 3. So very similar to the blood vessels in our body, but it is a lot more complicated, like you see. So he wanted to analyze these, and he was doing this on a computer desktop again, like we all have. But what we wanted to do was bring him to a cave, or maybe add some 3D interaction and see if that can help him. So we ran a study, and again we found some results with the cave, which extended our previous findings, which I'm not going into the details, but I'll move on to the next part of my talk, which is about the 3D interaction designs that we built with him. So I'll just quickly move on. So we raised some questions, some were answered, and currently we are actually running a study with a collaboration between Brown and Virginia Tech, where we are using the yurt of Brown and a cave at VT, and also an HMD at VT, to see if the platform independence of the results are still valid if you use some other data sets. So it's a lot of things going on, but maybe it will become more clear during the end of the talk. So during my work at Stony Brook, a very similar thing came up, where we are looking at this resolution which this hardware allows. So this hardware is called the reality deck. Yeah, the reality deck at Stony Brook. So it has these 1 billion pixels in a room-sized display, which gives us a lot of pixel size or display resolution to play with, and we wanted to see what are the effects of increasing these megapixels, right? So we have a computer screen with 1080p or 720p, but how about we have 300 megapixels or 600. Does it really matter? And how does it help us, or really does it help? So we ran this study and we found that if we increase the resolution for information visualization, so InfoVis datasets are datasets that we get, let's say, from Twitter or from any news agency which is not tangible, like in 3D, but those are more like text-based or intangible information that we can map on a computer screen or such displays. So for those data analysis, we looked at increasing this resolution, and we found that the resolution increases help up to 600, but above 600 megapixels up to 1 gigapixel, it really, it actually doesn't help. It gives some negative results. And we speculated why those happened, but we were getting more into the cognitive side of things. So increasing the cognitive load in the mind and looking at such, so many things at once might be a lot more overwhelming. So all those things, maybe some future work, and also some cancer-related research that I was involved in. We're looking at these scans of the colon of human body for virtual colonoscopy, and we again found that using a desktop is not that beneficial when you also have some other immersive hardware that we can use. So again, not going a lot in the future directions right now, but we have these haptic and other audio displays coming out, as well as olfactory displays, more from Japan, that are coming out, which does not only allow us to smell funny stuff that they had in their papers, but also maybe if we are transported to worlds that has different kinds of smell, how that can help, or a lot of ways to find out or explore more about VR. Recently, you must have heard BCIs are coming out. So EEG or fMRI or fNIR scans, which allow us to know what is going on inside our brain in real time. These can be used in many different ways. So adding those to 3D interaction or just communication over the network. You must have seen Washington from the University of Washington, they did some recent work where people could talk across miles just using their thoughts. Anyway, moving on to the 3D interaction side of my work. So this is a data set of the fossil that I was talking about. So as you can see, there is some kind of boundary, hazy boundary, which comes up as we move through in 3D. So the questions that the scientists were interested, those were these kind of cells. He wanted to see how many of those cells were there, if there were intercellular bodies, can we count those, and where those intercellular bodies are with respect to these cells, more to the center or towards the boundary, things like that. And he had to manually clean these data sets or automatically using some segmentation and then analyze these structures. Now we asked, if we add some 3D interaction, can those be helpful? There's some prior work which has looked at this before. But we worked with him to find out the usability criteria of this 3D interaction design. And then this was our first design that we came up with, which used a display wall, but we had this wand where you can just grab and move things. So this is not the fossil data set, but this is a very similar artificially generated volume data set. And here you can use this technique where you can use your hands to just grab and break it, like in real life we do break a bunch of stuff, like a fruit we want to break and eat, things like that. But here it also allows us to join those back. So if you have broken a piece and if you want to see some stuff which is inside but which is also broken, you can join those together and then break it in some other way where you preserve that. So this was an artificial data set, and we analyzed and got some results. But then we wanted to see how it looks with real data sets, right? So we worked with Jake, who was analyzing these scans of the carabid beetles. So these are symmetric design, where the two hands work in symmetry. Like if you're driving a car, two hands are working in symmetry. So that was our first design, because we thought that two hands working in tandem might be more helpful than asymmetric designs. But we soon were proven wrong, because when we iterated with the researcher, he found it really hard to use his two hands, simultaneously in a similar way. So our next design we identified all the problems and we changed it to an asymmetric design. And there are existing theories. So Giard's framework from 1987 talks about what are the postulates for doing a good design with asymmetric interface. So we took some of those and we also thought about additional usability criteria. So here you can see the left hand is being used to rotate, and the right hand actually allows us to break. So not worrying about two hands to break, but just breaking down these interactions in rotation or movement and breaking differently. So you can see this data set is working in real time with just a basic computer, not even a very high class system. But this simple way of breaking this and analyzing this in 3D helped him a lot. So we ran a study comparing this with two other previously designed techniques. So in 1994 or 96, that time frame, technique was designed for analyzing neurological data sets, human brain data sets, and that is called arbitrary slicing. So as you move your hand in 3D, you can see the slices of a brain on this kind of screen. So exactly the same technique we designed for analyzing this beetle, which we called arbitrary slicing. And then another design which is widely used. So if any of you is a radiologist or a doctor, you should have used this, which is axis aligned slicing, which is along the 3 axes, orthogonal axis, and you just slice the data and see the parts that are internal to the data set. So we compared these 3 techniques and we found that our technique that we designed was significantly better in a bunch of different tasks. So again, not going into the details, but this study showed that this kind of cracking or using 3D interaction might be a lot more useful. So going into the future, we designed a lot of ways to do segmentation, which is a standard issue with analyzing these data sets. So we are still working on those, and these are some quick prototypes. You can see how good I am at sketching. This kind of different novel and technique designs that we thought about doing. So we'll probably be pursuing very soon. Now, using these natural or magic interactions, are those really useful? So there are a lot of articles over the years that has talked about how magical the interaction should be, how natural should we get to the real world interactions, are they really useful or not? So a recent paper I have cited this year, because this has shown, is coming out from Autodesk Inventor, which has this CAD software which some of you might have used. So they found that if you switch between 3D and 2D in real time, that actually helps in doing some tasks when you have 3D interaction as compared to 2D interaction. So in certain cases 2D interaction works with 2D displays better, but in certain cases 2D interaction works with 3D displays better. But it is also the other way. So there is some confusion going on, but it is not that easy to answer that, we understand, but it is more of a future focused research. And there is this kinesthetic frame of reference, which I can previously have found. So if I close my eyes, I can still use my hand in useful ways. I can grab something. So this means that my hands work in its own frame of reference, which can really add to my visual frame of reference or can have a conflict to it. So matching those frames of reference, interaction and visual frames of reference, can be useful in certain cases. It can reduce some cognitive load for certain tasks. It can add to the cognitive load. During my IBM internships, we found some of those. But then we can also switch to some sequential style of interaction. So just moving on to the last part of my talk, which is using the task taxonomy or the theoretical work that we did. The reason for doing this work was we were working with these scientists from many different domains, and we were finding the results which are tied to the specific domains. But then when we talked to the other scientists, we mentioned, we ran this study last quarter and we found these results, and these were great. We published a paper. So he came and told us, why don't you run studies with our data sets? We said we had problems because it takes some time to render. Rendering on the cave is a lot different than a desktop. So we wanted to have portability of the results across the domains. So the biomechanics scientist, when we talked to them, we wanted to tell him, okay, so we found these results, you can also use these. You don't have to wait till we run study with your data sets. So that gave us this idea that how about we design tasks which are very fundamental and span across the domains. So we hypothesized that a few abstract task categories can really capture the benefits comprehensively across multiple domains. And with this, I just published a paper. I went to Chicago at the IEEE Visualization Conference, which is the biggest conference in visualization since 1988. And I just gave this talk this last week, which talks about how we can use such an umbrella of tasks or task taxonomy at an abstract level to generalize results in different domains. So the way we proceeded was we presented an initial position paper at a workshop, and we found out that there was a lot of interest with this kind of theoretical work across many different domains. So that led us to work more, and we came up with this initial framework, which we presented another paper. So after the design that we had, the slide should have been switched. We ran a study during 2013 where we reached out to people across the globe through various professional listservs like the SciVis listserv. There were many other Kyle listserv, computer human interaction listservs, virtual reality listservs. So these are listservs which you can reach out to people across the world who are interested in that domain. So these are all professionals, not only in academia but also in industry, but these are serious people who are really interested in this kind of work. So luckily we had 167 respondents, which to us is a big number, because in studies like this we usually get like tens of people. So 167 people, and they self-reported to be coming from 10 different scientific domains. So and we wanted to validate this design that we had. So this was our design, this theoretical design. And what really this means, you can see this has this basic task categorization. So just imagine a search task and how we can map it across domains. So let's say a paleontologist is looking for these fossil samples, and how those are structured. So the cells inside a fossil. So he's looking for the boundaries of the cells, tracking those boundaries, right, in 3D. A medical biologist is looking through this lower left limb of a mouse, and is looking at how the blood vessels are running in 3D. And again, this biomechanics scientist, he is looking inside this body of a beetle and looking at how those tracheal tubes run in 3D. So they are all kind of doing a spatial understanding task, which is following a path in 3D at an abstract level, right? And similarly, we had this pattern recognition mapping, the search mapping across all those domains, and we did all this work, and we refined this outline. Initially, we had 7 such tasks, but over time, this filtered out and became these 5 categories. So these were our basic tasks that we had across these multiple domains. Now, when we wanted to run studies based on these tasks, these other supporting tasks came up, which we also listed, but these were not like empirical tasks we wanted to evaluate. But this was the whole design. These box plots show that they were validated quite well. The 4 was the average level, and 25th percentile is above the level 4, which to us shows a pretty strong agreement to our design. So this was accepted quite well, and we just published it, so we are going to use it. Now, how does these 3 lines that I talked about go together? So this is where I think it gets more interesting. So we have some results talking about that if we have more immersive displays, we can have benefits with analyzing data sets. If we have some 3D interaction techniques, that can also help. And if we have some tasks that can actually understand or tell us that which of these components of display or 3D interaction techniques benefit, we can generalize those across domains. Now, we really want to put all of this together in a 3-way mapping. So let's say we know that some results here are beneficial for this, we know some results here are beneficial for this, but if we put this together, then we get a system that we can use, right? So a system won't have just a display, it will also have some interaction. So this 3-way many mapping is what we envision getting at maybe years from now. But that is a kind of a grand vision. And giving you an example, and this can lead us to in our rest of the time some design of some games or things like that. So let's in a neuroscience domain, typical challenging task is to find out all these floating heads. So these floating heads are the heads of the neurons in our brain. So we have these billions of neurons shooting shooting up every second. So in segmenting these data sets at the level of scans that we have, we don't really always get to the level that we want. So we have these floating neurons, which are like floating heads, and we want to connect them back to the main neuron that it came from. So this is kind of a path following that the neuroscientists talk about. So if we have some results tying path following to, let's say, the display that we have, some 3D interaction that we have, then we can say if you design a system for the neuroscientist and the neuroscientist doing a path following task to tie the neurons, then this system will be a lot better than just using a desktop. So that will be sort of a goal for any domains that we have. Okay, so with that, I'll just thank all my sponsors and my universities over the years, and these people who have worked closely with me. And probably this slide misses many names, but I just appreciate all their help over the years. So with that, I'll thank and take your questions.